but so does the risk. So value at risk, if I shift the mean up, it actually reduces the value at risk. Okay, I mean, yes, it reduces the value at risk. These are useful for a lot of things, but they are not useful for trying to optimize a trade-off between risk and return, because the two things are not independent. There are a whole class of portfolio optimization techniques that say, actually, we don't want to optimize mean variance. Let's, in fact, instead optimize mean var, which could make sense. What doesn't make sense is to draw it in a two-dimensional space where those dimensions are orthogonal, because the minute I shift one, I shift the other thing at the same time. What I want to do is to find a deviation risk measure that is to exponential utility what variance is to quadratic utility. I want to find the parallel measure of that. One thing that is worth saying, too, is if I take any utility function, expected utility itself is a generalized risk measure if I put a negative sign in front of it. Because what I'm effectively doing is saying, as I shift this up, the expected utility increases and the risk decreases. So you could actually see the expected utility itself is the inverse of a generalized risk measure. Fairly technical detail, but could be interesting. So let's look at a bunch of risk measures out there. Volatility, or standard deviation, in psychological terms is a very poor risk measure. Why? Because what it says is that, imagine I have a distribution of outcomes. It says, as things get better and better and better from the mean, as things get worse and worse from the mean, what I'm going to do is those outcomes increase the risk of that distribution. So the more stuff I've got further away from the mean on the downside, the higher the risk of the distribution. However, standard deviation also says the more things I've got further away from the mean on the upside, the more it increases the risk of the distribution. So you run the risk of going out and saying, I'm terribly sorry, but there's a horrible chance you might get 4% more than you expect next year. But don't worry, we're measuring this in our risk measure, and our optimization procedure is trying to suppress the chance of that happening. This is not what risk means to people. Risk is the chance of something negative happening. So in psychological terms, we can think of standard deviation or volatility as if this y dimension here is its contribution to psychological risk. Various outcomes, as they get worse, contribute more and more to the risk, and as things get better, it contributes more and more to the risk. It's a risk measure, but it's not a risk measure that has any parallel in human psychology. VAR is an equally weird risk measure. Actually, this is CVAR. But VAR says, actually, all I want to know is the value of the distribution such that 5% of the distribution weight is below that amount. And every risk measure I choose implies something about what I care about as an investor. So if I choose VAR, what it's saying is I don't care about the shape of the distribution above this 5% point at all. And once I've got to that 5% point, this is CVAR, I care equally about any shape of tail below that. I could have all of the weight just here, or I could have a really long tail with some catastrophic outcomes, has the same VAR measure. So VAR is insensitive to all sorts of aspects of the shape of the distribution. CVAR. VAR itself actually is a single spike. The implied utility function of value at risk, not conditional value at risk, is that all I care about is a single point of the entire distribution. So value at risk, let me, I'm going through these quite fast now. If I have a distribution of outcomes, a 95% value at risk basically says what I care about is the value here such that 5% of the weight of the distribution is below that point. Okay? So if I shift this distribution up, that value gets higher and I have a lower value at risk, etc. Now, if I was to change the shape of the distribution of returns, and I was to go, actually, what we've got here is a distribution that instead of the one you've got does this, and then it's got a huge pile of possibilities of a really good outcome down there. And over here, this tail is really, really long, so there's a whole bunch of catastrophic stuff that can happen. I can change anything about the shape of the distribution above this point and below that point, and it doesn't change the risk measure at all. So it means that if I'm using that as an optimization, it means that the assumption I'm imposing on human psychology is that people are absolutely insensitive to these sort of massive changes in the distribution. They just don't care. What I want to be looking for is a risk measure that does this. It says, yes, like standard deviation, I want to use the whole distribution. I don't want to throw away information like they do in value at risk. As things get worse and worse and worse, I want to penalize those outcomes because I don't like bad outcomes. I want to have outcomes down here add a lot to the risk so that when I minimize the risk, I suppress the chance of those outcomes happening. But good outcomes should actually reduce the risk. If I've got a chance of a good outcome, I want to let those things in. I don't want to suppress them. So what I would ideally like is a risk measure that is asymmetrical and its contribution to psychological risk, to the weight of that outcome in my psychological risk looks like that. And if I was a really low risk tolerance person, I would penalize negative outcomes much, much more, and I'd have less of an effect on gains. And if I was a very high risk tolerance person, I'd have a much more linear function. So that's what we would like to intuitively be looking for. And so the actual one we end up with looks a bit more like this. This is the risk function that arises out of an exponential utility function, which I'll get to the mathematics of it in due course. But it looks a lot like standard deviation on the downside, except that because it's exponential, the degree to which it penalizes the extreme downside is exponentially greater as the outcomes get worse and worse. And it makes good returns actually reduce the level of risk. The reason this is important is when I no longer care just about standard deviation as an individual, when I care about skewness and kurtosis, standard deviation doesn't reflect any skewness or kurtosis in the formulation. Whereas this risk measure, if I have two distributions with the same mean and the same standard deviation, this measure will additionally penalize investments that have high kurtosis and will penalize investments that have negative skew. So it's basically, we're packing into the risk measure adjustments for all of the higher moments of the distribution rather than saying, actually, let's just assume people only care about standard deviation. All right, so what we're going to do is we're going to find a way of replacing that. I'm going to finish, let's see how we go. Well, maybe I'm going to push on and then hopefully finish a bit earlier, I think, rather than take a gap now. Is that okay with everyone, or do we need a break? Okay, fine. So I want to choose a risk measure. I've already chosen a utility function. I want to choose a risk measure. Once I choose the risk measure, that will force me into a particular choice of indifference curve. So what do I want my risk measure to do? I want it to be independent of return. I want it to be a deviation risk measure, because the whole point of doing this is to draw a nice Markowitz risk versus return diagram that is intuitive and meaningful. I want it to reflect the shape of the entire distribution. I don't want this sort of thing where I can change the distribution massively and it makes absolutely no difference to the risk measure. So I don't want to throw information away, because that is irrational. So that counts out all sorts of things like VAR and CVAR and expected loss. Hang on, what happened? I'm going backwards. I want a downside orientation. Risk is the chance of something bad happening, at least risk as it's meaningful to people. We can define it. We can define that away if we want, but that's not a sensible thing to do in this context. So it should be consistent with having a concave utility function, which it will be because we have imposed a concave utility function. Risk is subjective. This is an interesting one. I would say this is less something we want to impose on the risk measure as something that actually pops out of the mathematics when we get there. If people have different levels of risk aversion, it may be that's because they weight different aspects of the distribution differently. And so I think this is probably, it is a desired property, but it wasn't one that we were looking for when we were actually going through the process to build this risk measure. It turns out to be a feature that arises naturally out of the mathematics. I would want to have, for all individuals, if I have a completely risk-free investment, so any certain thing should have a risk of 0. So my function should equal 0 as long as there's no variability whatsoever. And I'd quite like it to be easy to calculate. I want it to result in a usable risk-return trade-off function. Because if it's not easy to calculate, I may as well throw away all this stuff and just go back to, I've already got a utility function. I can find the optimal point, the optimal portfolio. I don't need to do any of this. So if it's too difficult to calculate, then I'm going to throw it away. And ideally, this is a nice to have, ideally, I would quite like my risk measure to collapse to variance as a special case if the distribution is normal or Gaussian. Because I'm actually trying to build this as an extension or an enhancement to mean variance optimization. And we know that mean variance is the right answer as long as the world is Gaussian. So if I assume in my model that the world is Gaussian, I'd quite like risk to be measured by variance, because then I have a parallel or an equivalence between the two models. Now, I'm not going to go into this in extreme detail. I'm going to go through the intuitions of how we get there. The mathematical derivations are all in chapter 5 in here. But this was something that we were struggling with for a very long time. There is a paper by a mathematician called Bell in 1995 that for completely other purposes I was looking at when I was doing my PhD ages ago, and I sort of went back to it and thought, this guy's already done all of this. He's already found a way of arising at a risk measure that builds on this axiomatic approach, which was handy because we just kind of borrowed it and adapted it to the specific purpose. So what he had done was to say, let me look at a whole raft of different utility functions and use this mathematical mechanism to ask the question, what do these utility functions imply about how people perceive variability of a distribution? So if I have a quadratic utility, then variability around the mean means this sort of thing about risk. So he was actually doing all of this for completely different purposes a long while back. But where this gets us is we start out with a utility function that says we want to maximize the expected utility of log returns on total wealth, and the function that we want is that one, because it meets all the criteria we've set up for a utility function. I have, what I would like to do is to transform that function, instead of having to plug in the entire distribution of outcomes, I would like to transform this function so that I can calculate expected utility by plugging in just two numbers, the expected return and some measure of risk. And it turns out that expected return is expected return, so that's fine. If I fix this to be my risk measure, then I can rewrite the expected utility function like this. That says instead of using an exponential utility function, I can say that it is also equivalent to be maximizing this function of expected returns and this variation on variance, which we've called behavioral variance. And if that is the case, what naturally pops out is this is my function that optimizes expected utility. This, if you like, is a rewriting of the utility function, where instead of plugging in every outcome times by its probability, I simply look at the whole distribution, I go, what is the risk, what is the return, I plug it into this function, and it comes out with this. So it's a rewriting of the utility function in just two arguments, rather than having to plug in every possible outcome. Now, I'm not going to go through all of the mathematical derivation of this. There's one neat trick that Bell had. The rest of it is just simply algebraic manipulation and moving things around. So it's in there. I'm not going to ask you to demonstrate or prove that in an exam. That's not what we're trying to achieve here. I want to get across the intuition. But I would recommend reading through it just so you can sort of drum this in what is actually happening. We have a utility function. We would like to rewrite the utility function as a function of simply two arguments that are orthogonal to each other, so that we can also describe investments by these two arguments and put them in risk-return space. And when I do that, what pops out is a rewriting of the utility function that looks like that. Now what I've got is the ability to take any portfolios and represent all of the variability in that, not by variance or standard deviation, but by this risk measure, which looks like this. Now, why is that risk measure nice? Well, if I have an absolutely certain outcome in here, it collapses to 0, because every single outcome is equal to the mean outcome. So this entire term just collapses to 0, which means that if I have no variability, my risk equals 0. So that's one of the things I was wanting to look for. As it happens, this entire thing is a generalization of variance. So if I plug in any distribution that is Gaussian, in fact, any distribution that is elliptical, this collapses just to be equivalent to variance. So in a Gaussian world, this is variance or standard deviation if we take the square root. So we can think of this whole model as an extension that rewrites Markovits based on a better, more normative utility function. So we've got that. Notice, however, that it is subjective. I can have two people looking at exactly the same distribution of outcomes, and because this function is not independent of t, it is if it's Gaussian. If it's Gaussian, any two people looking at a Gaussian distribution will have the same risk measure, which will be the variance. If it's not a Gaussian distribution, this risk measure is not independent of t. That means two people with different degrees of risk tolerance might disagree on the relative risk ranking of investments in front of them. And the reason for that is people will trade off standard deviation versus skewness versus kurtosis in different ways depending on how risk averse they are. Yeah?
So if you're actually doing it in practice, how do you measure the risk of energy if you have a client? Like, how do you measure appliance risk?
Yeah, that took a while. I actually had a client organization ask me exactly that question this afternoon. I might postpone some of this because I've got that. I'm going to come to that. But what we do is effectively we say, so there is a mix of art and science to this. Part of the problem with this T thing is because when I observe people's actual choices, I'm not just observing their normative degree of risk aversion, I'm observing all the other behavioral stuff that comes in. This is actually unobservable through behavior. It's reflected in behavior, but there's a lot of noise about it from all the other stuff. So I have to find ways of triangulating it. So I can't measure it directly. I can't get a clear-eyed assessment of it if I give people lots of choices and watch their choices, because what I'm seeing is a blurred muddle of their t-value with a whole lot of other stuff, frame dependence, et cetera, coming in. So what we actually do is a few things. One is we can ask the question, what does the industry think it's reasonable to give in terms of risk-return trade-offs to people who fall into different parts of the spectrum of really risk-averse to really risk-seeking? So we can use that as one triangulation point. So just for example, if I was to say, for someone who's absolutely down the line moderate risk aversion for their total wealth, imagine I had a portfolio that, what would be appropriate for them? Probably something in an equilibrium sense that has a risk level, an annualized standard deviation of around 10%. And I can look at what sort of returns I would expect to get for that over long periods of time. And it may be that I would expect to get over long periods of time an excess return over cash of about 4%. So what I have here is a Sharpe ratio of 0.4. So we can say, if this, for example, this is probably pretty close to a standard 60-40 equity bonds portfolio over very, very long periods of time. And if we can agree that that is a good thing to triangulate around or to anchor on for an individual who's moderate risk aversion, then I can start to say the Sharpe ratio for the portfolio we believe to be appropriate for them looks like that because I've got 0.4. And in order for that portfolio, this is the 10% line, in order for that portfolio to be right for them, their risk, the slope of their utility function would have to be equal to the 0.4 slope at that particular point. So that gets me to a unique parameterization for T. So I can start to back out reasonable variables for T by looking at what is a reasonable amount of risk to give to people at various different levels.
So you assume that from a particular function?
I'm sorry?
You assume that function?
Yes. So I say, if this is all about the long term and not about people's immediate responses, I can assume that function because that is the expression of a normative long-term thing to have. And I can then ask, what do we think it is, what is our best guess of the range of things that is reasonable to give to that person versus another person? And I can use various ways of getting that to back out a value of T that would make that the appropriate choice.
Do you actually ask them, or you say what you think they would say? Like, do you actually ask them what do you think is reasonable, or you think what you think?
We're doing what we think, because if I ask them what they think, I get a huge amount of noise back again. So that's one way of doing it. You start to look for anchoring points that you think are reasonable. The other way of doing it is we can start to look for very simplified gambles that we can use to test the reasonableness of things.
Okay, so like, what would you do if I was giving you this money?
Exactly. So if I was to say you have a gamble that is 50% chance that your wealth will increase by 40%, okay, this is an extreme example, and a 50% chance that your wealth will decrease by X%. Now, that sort of gamble, there is a unique answer to what X is for every possible value of T. So I can start to back out and say, okay, I've tested this against market-type portfolios. I can now test it against a whole range of simplified gambles and ask if that still makes sense in that context.
Okay, so you ask them for X, and then you tell them, okay, that's your T.
Yeah, basically, yeah. Although I would never do that at an individual level, because when you ask, what we would do is ask a whole bunch of people in a controlled environment what X is, and we use that to calibrate. We use that to calibrate T in general. So what we start with is this is sort of getting. Well, I'll continue. What we start with is a psychometric test that basically puts people on a relative scale.
You do that for people who want to invest in a company, like in an asset, like everyone does it.
I'm sorry. So
Everyone has to do it. Like if you want to, like an investor, you have to take a test.
yes. So risk tolerance test, effectively. So what this is using a series of psychometric techniques that are question-based that will isolate not what the right risk level is to you, but how risk tolerant you are relative to the rest of the population. From that, I can chunk this up and I can go, all right, I can identify a pool of people that is like group 1, group 2, group 3, group 4, group 5. I then go and I run an experimental environment where I put people from these different groups into here where I ask them about X. And I'm using responses in a sort of clean and clinical environment to try and attribute a value of T to every one of these populations. So there's a whole lot of different ways of getting it. All of them involve a little bit of guesswork and a little bit of measurement, because there's no real way to absolutely measure T, because behavior that we observe always muddles T in with other stuff. That is one of the more difficult questions. This sort of stuff, I think, is very much at the fringes of the industry's ability to provide a rational argument for why we give anyone a given risk level. So the sort of things that we're talking about there are actually very much under discussion and development in the industry as a whole. And it's, I think, a very difficult question to which we have a range of answers that we think help to get us in the right place, but there's probably more refinement to come. Where are we? Okay. So, different individuals looking at the same set of distributions may come up with different orderings as to how risky they think they are, because some people will penalize kurtosis and skewness more than others. In particular, people with a low t-value, so people with a very concave function, will place a greater weight on negative skewness and kurtosis than people who have a more linear utility function. But what this is doing is it means that our risk measure is not just measuring the first moment of the distribution. It is adjusting that measure for every single higher moment of the distribution. And it can account consistently for any type of distribution, including those that are extremely non-normal. So if you had an asset that basically said, or let's just take if you had a high-yield bond, for example, where your distribution of outcomes actually looks like there's a value distribution, and then there's a chance of default, and actually you've got a bimodal distribution where if there's no default, you're going to get an outcome something like that, but there's a high probability that you'll get a really negative, a really bad outcome. Actually, measuring that by a traditional standard deviation measure tells you very little. In this one, it uses that whole distribution and it adjusts the risk measure to account for all sorts of really non-normal aspects of the distribution. And so what we end up with here is we replace that with this behavioral standard deviation, and we can move once again to say, okay, we want to not just maximize expected utility, but we want to understand how that maximization is a function of expected return and attitudes towards all the variability of the distribution. And that is the function that trades the two off. Now, the last step in this is that that function, because it's a utility function, still doesn't give me anything in numbers that are meaningful to me. I put in any distribution, it'll spit out a number, but the number itself doesn't have any meaning, and that's because utility functions are not unique. I can morph any utility function by a positive affine distribution, which is to say that the utility ordering from function u of x is exactly the same as the utility function for any other function that might be c plus alpha u of x. So the units that result from utility optimization are not unique. They're pretty arbitrary. So here I can draw things in risk-return space, but the actual number that spits out of this function doesn't mean very much. What we want to do is to try to turn that into a measure of expected utility that is meaningful to us. And the way we're going to do it is to say, let's look at a few points on this distribution. Firstly, if I have, in an idealized world, I have a risk-free return, I can say, all right, risk-free return, I know what the return is, I know that the risk is 0 because it's risk-free, so I plug those numbers into this function, and that is my formula for that portfolio, the risk-free portfolio, as it were. I can then ask, I'm not going to be indifferent between the risk-free portfolio and any other portfolio, but if I start adding money to the risk-free portfolio, there will be a point at which I am indifferent between an enhanced risk-free return and any other portfolio in this space. And I may be down, it may be up. But what I can do is I can say, let me find this point such that the utility of that is equivalent to the utility of that. Okay? And that point I can reflect by a function of risk-free plus a further risk-free amount, which we will call D. And again, it has 0 risk. So the formula for that is this. It's the same as this, but I've just added this amount D to it. Now, I can vary D up and down until I find a point such that it is equal to the expected utility of any other point in that. And when I do that, what I'm doing is this. I'm saying, let me take any distribution, any portfolio or any asset that has an expected return and a risk level, and let me make it equal to some risk-free point with this free parameter D that I can vary up and down. And I can plug in those formulae because I have the formula for this point, and I have the formula for this point. I plug those two in, I simplify, and what I end up with is this, which looks very similar to the Markowitz risk-return thing, just with small